Last time we got into chapter 12 here, which was kinetics. So as we talked about, kinetics really deals with sort of the study of kind of how fast or slow a reaction takes place. Remember that, as we'll talk about a little later on in the semester, thermodynamics deals with whether or not that reaction will sort of take place. So we look at kinetics a lot of times as looking at sort of the change in the concentration of a reactant, a product, whatever it may be, over some unit of time, which obviously gives us a rate. And one of the things that we talked about last time was sometimes referred to as the rate expression. And the rate expression allows you, if you have an equation such as this, if you have an equation such as this, if you know like one piece of information, be it the average rate, be it how a reactant is changing with time or a product changing with time, you can really use the rate expression to figure out basically how everybody else is changing with time. So we could write something like the rate is equal to minus 1 over the coefficient, which is A. And again, we're going with minus here because this is, again, a reactant, which means it should be decreasing with time. Change the concentration of A over the change in time. That would equal minus 1 over B, change the concentration of B over the change in time. That equals, when we get to our product side, 1 over our coefficient there, C. Change in the concentration is C over the change in time. In this case, we do not have negative as it is a product and it should be increasing with time. And lastly here, we could do 1 over D, change in concentration of D over the change in time. Once again, product, so no negative there. The point of really the negative again here with our reactants is, as we talked about, this rate should be usually a positive number. So because, for example, here A and B are decreasing with time, what will ultimately happen is when you do your kind of change in concentration, which is what those brackets mean, take your concentration of A final minus your concentration of A initial. Because it's decreasing with time, your final will be a smaller number than your initial. And when you do that part, you will get a negative there for the change in concentration, which with this negative up in front will turn it into a positive, as opposed to here on the product side where you do something like the change in the concentration of C final minus initial. Because it's increasing with time, our final will actually be a larger number than the initial, and that will yield you a positive number, which means, again, you don't need the negative there to turn it into a positive. So you can use this again to relate basically anybody in the equation or reaction, as long as you know really one piece of information. Also, we do 1 over the coefficient from the balanced equation, and what that takes into account and sort of helps you along with is sort of the mole-to-mole relationship, the stoichiometry that's involved. And again, as we saw, I think on the very last example, in a lot of cases, you can do just a regular kind of stoichiometry problem first, and then kind of do the kinetics part of it. Or you could kind of bundle it together here by taking 1 over the coefficient to do so. Any questions on any of that there that we talked about? Okay. Also, as we mentioned, since they're all equal to each other, if you were just interested, say, in A and C, you can write individual sort of rate expressions for each of those. And what really, again, sort of ties them together is the rate. So, for example, maybe you do have information about A that would allow you to get the average rate. Once you have the average rate, that would be this rate. And then that could allow you to figure out basically how, for example, C is changing with time. As we also talked about last time, again, the rate should be positive. But if you are describing sort of the rate of how a reaction is disappearing over time, you can and should probably end up with a negative number to indicate that it's decreasing with time. If you're talking about sort of thank you, sometimes referred to as the rate of appearance of a product, you'll end up with a positive number for somebody on the product side. And sometimes, again, it's referred to as like the rate of disappearance for a reactant. And again, that can be negative. Any questions on that there? All right, so I think where we left off was here. Let's talk a little bit about some of the factors that affect the rate. And some of those factors are the nature of the reactants, And that means basically what kind of reactant molecules are present. Um, Small molecules tend to react faster than larger molecules. Again, smaller molecules are going to probably move around a little bit longer than uh, bigger molecules. Also, when we talk about solids, powdered solids are usually more reactive than sort of block solids. Again, there's a lot more surface area for everything sort of to react upon. Certain types of metals, for example, are more reactive than others. Kind of like when you do single replacement reactions, remember that whatever may be coming in that type of reaction needs to be more reactive than what is replacing. You might remember an activity series, maybe from Chem 50. It's a bunch of list of elements, hydrogen somewhere in the middle. And typically everything higher than list there is more reactive than a lower on the list, so that reaction will take place. Anything kind of lower on the list will be less reactive than a higher on the list, and that reaction would not take place. Ions also react faster because there's no bonds to break. Also, in case you're not familiar with, you typically always find ions in solution, which means they're floating around ready to go, ready to react. They don't need too much to happen. And they're also going to probably come in contact with each other a lot quicker. Another really important sort of factor in terms of the rate of reaction is temperature. Increasing the temperature typically will increase the rate of a reaction. The general rule is if you go about 10 degrees Celsius higher in temperature, the reaction will kind of double the speed of it. And that's for a lot of reactions, not all of them, but it's a kind of a general rule of thumb. The opposite is true as well. If you kind of lower the energy, the reaction will slow down. As we will talk about in this chapter a little bit, there is this like hill, if you will, that the reactants has to climb to get to the products. And a couple things happen. Obviously, when you increase the temperature, obviously increasing the energy, and that will give a lot more reactant molecules enough energy really to get up and over that hill to the other side. And vice versa as well. If you kind of decrease the temperature, what's going to ultimately happen is you'll have a smaller proportion of molecules that have enough energy really get up and over this energy hill to get to the other side. That's what's known as activation energy, as we'll talk about. But it's basically the hill that has to be climbed to get to the other side. And also, if you just think about it, as we'll also talk a little bit about in this chapter, for a reaction to take place, basically two things has to happen. There has to be a collision, and they do have to collide with the right amount of energy. So by increasing the temperature, you get everybody with a lot more energy, and they're moving around a lot faster than they would at lower temperatures. And that's going to obviously cause a lot more collisions and greater chance of product formation. There's actually an equation we will see later on that relates the activation energy, which is that energy hill, and temperature and the rate constant. Now, another way that you can sort of increase in most cases a reaction is by using a catalyst. And a catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. So a catalyst is essentially there to facilitate that reaction, again, in most cases, to speed it up. So it finds an alternative pathway, a more efficient pathway, if you want to think about it that way, for that reaction to take place. The end result of that is because it's a more efficient pathway, you're going to get a lot more products formed in most cases because not as much energy is needed for those reactions to get to their side. Ultimately, what a catalyst does, as we will talk about, is it's able to lower that hill that the reactants has to climb to get to the other side in terms of energy by finding this alternative pathway, and that allows more reactive molecules to get to the other side, and because of that, that's going to give you more products and usually speed up the reaction. There are also catalysts that are sometimes referred to as negative catalysts, and those are actually used to slow down a reaction. But I would say probably almost 100% of the time, If somebody's asking you about a catalyst or something like that, they're probably most of the time talking about speeding up a reaction, but there are some catalysts that can slow it down. There are catalysts that are homogeneous, just like a homogeneous mixture. It means that the catalyst is in the same phase as what is reacting. Heterogeneous as well means that they're in different phases. You typically, for example, in an equation, will typically see the catalyst written on top of the arrow. Maybe H plus, which means like an acid catalyst, maybe some type of metal like platinum or something like that, that is being used as a catalyst. But a lot of times you'll see that on top of the arrow in an equation written when you look at it. Now, how does this work? Again, like I said, it can be something as simple as you have some gas molecules that are just flying around, for example, and they want to react with each other. But again, in order for them to react with each other, they do have to sort of come in contact with each other and collide. So just by them just flying around, you know, you got to kind of wait for that opportunity to sort of arise. So you could slap in, for example, like a metal where it may attract both of those gas molecules towards the metal, and now they're going to be in much closer proximity to each other. That's going to increase the chance of collisions happening, and probably going to have a lot more collisions than if they were just kind of flying around hoping to hit each other. Everybody's going to be in the same location, and sometimes even the metal can sort of facilitate a little bit the sort of transferring and the breaking of bonds and making them new bonds as well. So that's one way a catalyst can kind of work, is just to provide sort of the right environment for everybody to come together again in a really more efficient fashion to make that reaction occur faster. Now, in terms of concentration, generally, the larger the concentration of reactant molecules, the faster a reaction will happen. It also increases, obviously, the frequency of reactant molecules coming in contact with each other. By the way, when we talk about molarity, the real definition of molarity is moles of solute, right, over liters of solution. And a solution, as you may remember, is made up basically of two things. It is the solute and the solvent. And when we talk about a solution, which a lot of times we look at in terms of reaction rates, it is the solute that is what is reacting. So it is really the solute that's actually reacting and available to react. So when you think about molarity, the only way you get large molarity is to have a good amount of solute present in the beaker or whatever it may be. And because you do, you then will have a greater chance, obviously, of reactions to taking place. Concentration of gases depends on partial pressures of the gases. The higher the pressure, the higher the concentration. As you may remember from your friend Boyle, perhaps, right? As the pressure goes up, the volume goes down, right? There's sort of an opposite relationship. So at higher pressures, what you're going to have in terms of volume is smaller volumes, which would then obviously put your gas molecules near each other and in proximity to each other. And that's going to allow, obviously, for the reaction probably to take place at a greater rate than it would if it was a lower pressure with a larger volume, where now you have the gas molecules again kind of spread out a little bit, and they're going to have to sort of rely upon sort of collisions to sort of occur. Questions on that there? So again, these are all factors that can have an effect on the rate of the reaction, either positive or negative sort of effect on the rate of a particular reaction. So the next thing we're going to talk about is the actual rate law, and the rate law expresses the relationship of the rate of reaction to the rate constant to its concentrations of reactants raised to a particular order. So when we look at this reaction here, this would be considered the rate law here for this reaction. And a couple of things, first off, that we see in here is when you look at a rate law, it is all about reactants. So there are usually no products in a rate law. It's all about what's happening with the reactants. And that's different than a rate expression that we talked about earlier, where we kind of relate everybody to each other. Here in a rate law, it is all about those reactants. This is our rate, which is typically in something like molar seconds. This is our rate constant. And then remember earlier on last time, that is the value in a reaction that is a constant value. Um, and these are obviously our concentrations here of A and B. Usually these are molarity. Now, X and Y are what are referred to as the orders. And X, for example, in this case, is the order with respect to A, and Y is the order with respect to B in this case. If you add the orders together for all the reactants, that will give you the overall order of the reaction. By adding, for example, X plus Y will give you the overall order of this particular reaction. Now, what are orders? You could think of it as sort of the proportion you need of like A and B in this example to react to give you a certain rate that's achieved. And knowing something like the orders and the rate law can really help you, for example, if you're doing a reaction and you know the rate law and you know kind of the orders, perhaps you're doing an experiment or want to do an experiment, for example, and maybe that experiment just happens too fast for you and for you to take your measurements or whatever you're trying to do with that particular reaction. So you could use something like the rate law, for example, to try to slow it down. You could also do the opposite of that. Maybe you're trying to do this sort of a reaction and it's just like taking forever. You could use the rate law and the knowledge of the rate law and the proportions of A and B or the orders as necessary to basically figure out how to make it faster. Based on the orders, you can sometimes determine that, based on the orders that you see, this reactant is a little bit more important in terms of the rate of the reaction to say the other reactant. Or maybe they may be equally important in terms of affecting the rate. And sometimes, like I said, it could just be like one only is the only thing that's really important. The other guy's really not doing much in terms of the rate. So, for example, if we look at the rate law, just to kind of give you, that goes away, maybe, yeah, we'll go this way. Let's just say, for example, we did have that rate law there. The rate is equal to K, A to the X, and B to the Y, right? And let's just say that we had the order for X was 1 and the order for Y was 1 as well. And we started with a concentration of A that was 2 molar and the concentration of B that was 2 molar, right? So if we put this into our rate law here, we basically get the rate is equal to K, and this basically would be 2 to the 1, right? And 2 to the 1. And this will give us a rate of approximately, we'll call it 4 molar seconds. This is a constant. We're not going to really worry about what the number is because it's not going to change for any of these here. So we got basically a rate of 4 molarity per second. So let's just say in this case, I decide, all right, what would happen if I decided to double the concentration of B? So in the next experiment, I run with this and I keep A the same, 2 molar, but I decide, hey, let's just double the kind of concentration there, B in this particular case to 4 molar. So if I put that in, my rate here would equal K, basically 2 to the 1 and 4 to the 1. My rate in this case is now 8 molar seconds. So what happened in this case, right, is I doubled the concentration of B. And what happened to the rate in this case? The rate doubled as well, right? So direct result. By the way, in this particular example, if I doubled A and kept B the same, you would end up with the same sort of result here. They sort of, because they both have the same order, are sort of affecting the rate the same. Now, let's just say, hey, like 4 molar per second is way too fast for me, right? So maybe I want to slow this guy down. So I go, okay, well, let me play with the concentrations and maybe, on the next one, I go with A at 2 molar and B at 1 molar, right? So now when I put it in there, I got a rate that's equal to K 2 and 1 to the 1, which is now 2 molars per second. I cut the concentration of B in half, and my rate actually dropped from the original one by half as well, right? So that is the relationship here. If I need to slow this reaction down, I can play with the concentrations. I could even play with concentrations of both of them, right? And cut them both in half, right? And then that would also have an effect. I would end up with something like 1 molar per second, right? And that's because they each basically halved, right, my rates. So I really needed to drop it. I could play with both of them. In this case, because the orders are basically the same for both of them, again, they're both going to sort of, if you want to think about it, equally sort of affect, in this case, the overall rate of the reaction. Because they are first order, which by the way would mean also the overall order for this reaction would be 1+1 or second order in this made up one here. And we'll talk about what a second order reaction is in a second or a bit. But again, by knowing the orders, knowing the rate law, you could use that in a practical effect to help you. Now, let's just say, for example, we had a different set of orders for a particular reaction. So I'm just going to kind of get rid of some of this here so it's more to the right. So let's just say in this particular case, we found out that for our rate law, we have the rate is equal to K, A to the 1 and B to the second order, right? And there's now second order in B, right? So if I just do my normal sort of starting guys like I did over here, where A is 2 molar and B is 2 molar, putting that in there, the rate is equal to K2 to the 1 and 2 squared. I now got me 8 molar seconds, right? Now, because our order in this case for B is actually second order versus first order in the first, you can see now we are starting out with a much higher initial rate for this reaction, right? We could also see that in this case, if I take my concentration of B and cut it in half to, actually, well, I'll increase it to 4 molar, actually. And we'll keep this A at 2 molar. We'll go with 2 to the 1 and now 4 squared. So that's now going to give me something like 16, right, times 2. They say that is 32, I believe, right? 32 molar seconds. Now in this reaction, when I double the concentration of B, how much did my rate go up by? A factor of 4, yeah, right? 32 divided by 8 will give you 4, right? So you're going up by a factor of 4. The same increase I did in the first reaction, right? I increased B by 2 by doubling it and only doubled it, right? So here we can see between A and B in this reaction, which one has a greater effect on the rate? It would be B, right? You see a much bigger thing. Because we could do the same thing with A. For example, if I took A and doubled it to 4 molar, kept B at 2 molar originally. Now we put that in there and we see we end up with 4 to the 1 and 2 squared. That's going to give me 4 times 4, which is 16 molar seconds. In this case, the rate did increase, but it only increased by a factor now of 2, right? So it only doubled the rate. So again, if you want a really big increase in the rate, you would want to play with B. If you want maybe a mild increase in the rate, you'd play with A. Yes. Do you have a question? Why am I what? Just to show you that this is the practical effect of the rate law and the orders. It allows you to know, for example, in a reaction, what reactant, for example, maybe has a greater effect on the rate of the reaction versus one that maybe doesn't have as much of an effect, or they may have, like in our first example, sort of an equal effect on what's happening in the reaction. And that's sort of the practical application of what the orders kind of help you understand. In this case, I doubled it just because I made up and doubled it. Is to answer your question, I could have tripled it, or whatever it may be. I just shown in terms of doubling the concentration. Yeah. Yeah, so are you asking how we get those orders? Yeah, we're going to talk about it in just a second. The short answer is no, they're actually not the coefficients in the equation. Yeah. So again, in this case, we could see that obviously B has a greater effect on it. And obviously, if we lowered the concentration of B, we would see a probably more dramatic slowage of the rate than if we did lowering the concentration of A. So those orders, allow us to understand how one reactant maybe affects the rate versus the other. Something that you also sometimes come across, for example, let's just say we had this situation. Let's say we had a rate law like this, which was the rate is equal to k to the a to 1 and b to the 0, right? So in this case, if I had my concentration of A was 2 molar and B 2 molar, and I put it in here, that would give me the rate is equal to K to the 2 and 2 to the 0. When you take something to the 0 order or 0 power up there, what does that equal? Equals 1, yeah? So this basically equals 1, right? And that would give me a rate of 2 molar seconds, right? Now, let's just say I took my A, right? And it was 2 molar, and I decided, hey, I want to really affect this reaction a lot. I'm going to make this reaction happen a lot faster. And I go, I'm going to make my concentration of B like 10 molar. Will that affect the rate of this reaction? It will not, because in this case, the rate is going to be 2 to 1, 10 to the 0, which is still 1, right? The rate's going to be exactly the same. You just wasted a lot of chemical, right? And you didn't get much out of it, right? In this particular reaction, because the order of B is 0 order, that means essentially it has no effect on the rate of the reaction, which means if you wanted to speed this reaction up or slow this reaction down, you would have to look at A in this case, because you can do whatever you want to be in this case. It's not going to affect the overall rate of the reaction. Any questions on sort of all that there? All right, so now to a really important question, which was asked a second ago, which is how do we get these orders? How do we get the rate law? Well, we do get the orders and we do get the rate law experimentally. So these are always found experimentally. And the orders are not taken from the coefficients in the balance equation. Now, that doesn't mean that you may end up with an order that is the same as what you see in the balance equation in terms of the coefficient, but that's not where we get the orders from. So because these are always found experimentally, what that means is you typically will be given a experimental table of information. So you typically will be given a table of information that, for example, will have the concentration of A, concentration of B, and some initial rates, are just really the rate is sometimes just referred to. And you'll have this table, and in this table, there'll be multiple experiments that you'll come across. So you will use information in these tables to mathematically calculate what the orders are of the reactions, of the reactants. Once you have, by the way, the orders calculated from the experimental information, that will then also allow you to actually figure out what the value of the rate constant is. So that's kind of the order that you do these problems. And these are typically the questions that you're asked, which is what is the actual rate law for this reaction with the orders? What's the overall order of this reaction? And what is the value of the rate constant? And the order which you want to do that is you want to figure out the orders first, get the completed rate law, then figure out the rate constant value. So let's take a look at one here. And just to kind of show you, this is a typical sort of table, for example, that you would have in a problem. And in this table, there's only 3 entries. Some tables will actually have a lot more, 4, 5, 6, 7, however many they want to put on the page. But typically you'll have also sometimes, in a column that'll say, hey, this is like experiment 1, experiment 2, and experiment 3, which is essentially what those numbers represent. So there's a couple of ways you could do it, but since you need to show your work, I would say for most people, the mathematical approach is probably the best way to do it. So to do that, you would take rate 2 over rate 1 equals K A to the X and B to the Y. or however many reactants you have going on there. You could have C to the Z if you like. Now, what does this mean? So this is not, for example, you go to the table and you just pick out number one, number two in the table. What you're looking for is to make the math easier for yourself, which means what you are looking for is you want to go to the table and you want to find two entries in the table, two experiments from the table where one of the concentrations stays the same in terms of their concentration, one of the reactants concentration stays the same, and one varies. Now, for example, if you have three reactants, you would want to go to the table and find two entries where two of them stay the same and one varies. So the idea here is just to have one variable. It's going to make the math obviously super easy rather than multiple variables, which we don't want. So for example, if we go to this table, I could clearly see in experiment 2 and experiment 1, the concentration F2 stays the same. They're both 0.1 molar, but the concentration of the other reactant actually varies. So that's probably where I'm going to start. I'm just going to write what I like to call just the generic rate law for this reaction, which is the rate is equal to K times F2 to the X and ClO2 to the Y. Once again, it is only reactants involved in the rate law, nothing to do with the products. So if I take experiment 1 and 2 in this case, I'm going to put it into this formula. Now, my piece of advice would be if you want prettier whole numbers rather than decimal type numbers, I would take a look at the rates of each of those, and I would take the one that has the larger rate and put it up on top. And that typically will give you kind of more whole numbers than decimals. Nobody wants to play with decimals. So in this case, if I look at it, it does look like experiment 2 here has the larger rate of the 1 and 2. That means up on top here, all the way across here, I'm going to put all the information I see in the table for experiment 2 up on top. So that is what I'm going to do. So let me put that in there. So we'll go 4.8 times 10 to the minus 3 equals K. My concentration of A in the second experiment is 0.1 molar, and that's going to be to the X. And my concentration here of the next one, 0.04 molar, that's going to be to the Y. So everything from experiment 2, I basically put up on top. Now what I'm going to do is take everything from experiment 1, and I'm going to put all that up on, or down on the bottom, I guess is a better way of doing that. So everything from experiment 1 will now be placed down here on the bottom, right? I'm just going to take all that information and pop it down there on the bottom. And if I do that there, I'm going to get 1.2 times 10 to the minus 3 K, 0.1 molar to the X, and 0.01 molar to the Y. All right. First off, any questions on that there? All right, now we're going to do some math. So 4.8 times 10 to the minus 3 divided by 1.2 to the minus 3. If you clear that out, that's a 4. All right. Now, this is the rate constant, and that is the rate constant. Although I do not know what the value of the rate constant is at this moment, it is a constant value, right? Which means should those numbers be the same or different? Which means they essentially will also cancel out, right? Because they're going to be basically the same number. I don't know what X is at this moment, this order, but I do know it's going to be the same because it is the same reaction, right? And under the same conditions. And that means that essentially these guys are going to also cancel out because they all should be the same. That leaves me just what I got going here on the right. 0.04 divided by 0.01 should give you 4 to the Y in this case, right? Now, in this case, you could probably just visualize that because there's a nice clean whole numbers there. Y should equal in this case 1, yeah. 4 to the 1 is 4, right? And that gives me 4 on each side, and they're equal to each other. By the way, if you did not have a nice pretty number on each side, maybe a little decimal-y, if you will, You could solve that by natural logging both sides. Yeah, that brings the y down, and then you could divide that to the other side, and that will get you your y value. So occasionally you may not get perfect pretty numbers there. You might want to kind of maybe has to do that. Also, you might have to do that if you maybe did not put the larger number up on top, you did the smaller number, you'll end up with some decimals, and it may not be clearly obvious to you maybe in some cases of what the exponent may be in that case. So you can natural log both sides and divide it to the other side, and that will get you there. At that point, if you do that and you're fairly close to a whole number, like pretty close to a whole number, you can probably safely just round to the nearest whole number if you kind of do that. Again, remember in real life, although we do a lot of book problems where they're kind of pretty numbers sometimes, and easy numbers, it is technically experimental type stuff, right? Which means you're not always going to get like nice, perfect, like 4 = 4 or stuff like that. So again, if you do that sort of natural log and you are close to a whole number, it is safe to sort of round it. First off, any questions on that there? So basically what we just found is the order with respect to ClO2 is first order. Now that we did that, what we're going to do is now come back to this table. And what we're going to do now when we come back to this table is we're going to do the same approach, which is I kept F2 constant the first time. Now I need to keep ClO2 constant again, just to give us one unknown. If you look at the table, I think you only have one option, which would be these two here. 1 and 3 are going to keep that guy constant while our F2 is varied. By the way, you can't come across a table where you have multiple choices, if you will, like experiment 1 and 2 or 1 and 4 will do it as well. And you can't pick any one you want. They should give you the same answer. So, there could be multiple sort of ones that you may choose to do so. So taking this here, experiment 1 and 3, I'm going to again choose the one that has the larger rate. And for me, it looks like 3 has a larger rate. So that's going to go on top. So everything from experiment 3 will go up on top here. And that's going to give me 0.2 to the x, 0.01 to the y. Everything from experiment 1 here will go on the bottom, and 1.2 times 10 to the minus 3, k 0.1 to the x, and 0.01 to the y. Once again here, doing our math, basically 2.4 divided by 1.2 is a 2. Once again, the k's are going to cancel out because they are the same. In this case, we already know what the y is, which is the same. It's going to cancel out. So here, this is going to leave us 2 to the x. And once again, here you could probably easily see x is equal to 1 in this case. And that would mean that this reaction is first order with respect to F2. It is also first order with respect to ClO2. Once we've now figured out the orders, we could write the completed rate law with the orders. And the rate law would be K F to the 2, and ClO2. Just like most things in chemistry, if you do not see a number up there, it means 1. And we typically do not write 1 for rate laws either for the orders. So again, if you see nothing up there, it is not 0. It is actually first order for each of those. Yeah. So again, we typically do not write in like the 1s here. So it's implied if nothing is there, it is first order. And again, not 0 order. If it is 0 order, by the way, you would either do one of two things. You would either write 0 up on top, because if you did not write 0 up on top, it would imply that it is first order, right? So you would have to, if you left it in there, write 0 on top. If you don't want to leave it in there, you could actually just take the whole reactant out and not include it in the rate law, because again, it's basically 1 anyway, so it's not going to be in there. So if you do have a 0 order on something, you either got to write the 0 in or take the whole thing out. Otherwise, if you leave it in with nothing there, it implies it's first order. That would mean my overall order in this reaction would be, my overall order is 1 plus 1, which is second order. And again, that is just adding each of the orders together. Now, the last thing that you typically are asked to sort of find in this type of problem is what is the value of the rate constant. So now that we know the orders, we actually want to now try to figure out what is the value of the rate constant. In this case, we have 3 experiments in the table, and you could actually choose any of these experiments to do so. Because it is a rate constant, no matter which one you choose, you should end up with the same number. So I'm going to choose number 1. And what I'm going to do is basically just put in my values in there. I'm going to take my rate law here and rearrange it and solve for K. So if I take my rate law, which is K is F2 ClO2, I'm basically going to take both of these guys and divide it over to the other side. And that's going to give me K is equal to the rate divided by F2 and ClO2. Once again, as I mentioned before, we're just going to get that information from the table. You could choose any experiment you like. You cannot mix and match those. So if you choose experiment 1, you have to use all the information from experiment 1, experiment 2, all from 2. So putting in our values here from experiment 1, that's 1.2 times 10 to the minus 3 molar seconds divided by my F2 concentration and my ClO2 concentration. And that is going to get me here 1.2 to the minus 3 divided by 0.1 divided by 0.01. And that's giving me a 1.2 as my rate constant. Now, what are the units here, right? So I got molarity up on top and a molarity on the bottom that's going to cancel. That will then give us 1 over molar seconds as the units associated with the rate constant. Or some people will write 1.2 m to the minus 1, s to the minus 1. So either way that you want to do it. The units for the rate constant are extremely important, and you should obviously always include units, but they are very, very important, as we will talk about. By just the units associated with the rate constant, it will tell you the overall order of that reaction, for example, is second order. Those are the typical units that you find for a rate constant for a second order reaction. And it's 1 over molar, some type of unit of time. It could be seconds, minutes, hours, but 1 over molar seconds are typically the units that you associate with it. Any questions on any of that? Yeah. You would actually use it both. So, for example, I think I know what you're asking. So let's just say, for example, obviously we didn't in this case, but let's just say, for example, that F2's order was second order, right? So we would have a 2 there. What that would affect, we do it the exact same way. What that would affect is when you come down here and obviously over here, that should be squared. So you would need to square the value of F2 when you come down through that. You would still do the same thing, and you would use in completed rate law. So that's why we want to kind of do it in that order, is to figure out the orders first so that you can get the completed rate law with the orders, and then you can use the experimental information, any one you want to choose, put it in there and solve for K at that point. And yeah, if it's a 2, if it's a 3, you know, whatever it may be, if it's a 0, you got to take all those into account when you're, for example, doing the calculation for the rate constant. Questions? Right. So as I said, that's probably the best way to do it mathematically because you do need to show your work. Sometimes people go, well, it doubled and it doubled, so it's like first order or something like that. So if you choose not to do that type of work, you need to, in words, explain why that is. So I think it's probably better just to do the calculation part of it. All right. Otherwise, you will not get credit for showing your work. So as we just talked about there, our rate laws are always determined experimentally. So you will always find yourself with an experimental table. The reaction order is always in terms of reactants. Products are typically not included. And in most cases, catalysts, for example, are not necessarily always included. Occasionally they are thrown in there as well, but in most cases, catalysts are not usually put in there as well. The order of the reactant is not, as an earlier question was asked, is it the coefficient? So we can clearly see in this example, the coefficient for ClO2 in the balance equation is 2. And obviously, it's only first order here when we talk about that. So we don't use the coefficients as the exponents. We do that in the next chapter and beyond. But in this chapter, we don't do that for rate laws in most cases. All right, so why don't you give this go? The rate equation for the reaction of NO with ozone is the rate is equal to KNOO3. if the rate is 6.6 times 10 to the minus 5 molar seconds, when NO is 1 times minus 6, and O3 is 3 times 10 to the minus 6, what is the rate constant? Why don't we change it up? Why don't we do something like that? Let's actually make it let's square just for the fun of it, O3. In this case, I changed it, so we went with the rate is equal to K, NO, and O3, and I decided to square it. Again, in this case, we would be solving for K, so we're going to bring these to the other side. So that's going to give us the rate over NO. And as we were just talking about, because I did make it a second order, we do need to take that over, and that would equal K. Popping in our numbers, they gave us the rate of 6.6 times 10 to the minus 5 molarity per second. And we have our NO, which is 1 times 10 to the minus 6 molar, and our O3, 3 times 10 to the minus 6 molar. Again, as I was mentioning before, in this case, because I changed it to second order, obviously here we would need to square that when we do that. Very commonly missed by people. It's like when they come to do the K is forgetting to kind of do that. So make sure you do. That would then give us, I don't know because I made it up. Let's see, 6.6 to the minus 5 divided by 1 to the minus 6 divided by, looks like 3 to the minus 6 squared. A big number on this one, huh? So he ended up with maybe 7.33 times 10 to the 12. And in this case, in terms of units, molarity on top and bottom will cancel. This will give us 1 over molar squared coming from here, seconds, yeah? Which, by the way, the overall order of this reaction would be what? 1 plus 2 is a third order reaction, right? Yep. Yeah. So you can see here the rate constant units are different than what we saw for a second order, which was 1 over molar seconds, right? By the way, this has how many letters? 2. Second order. This one has 3, basically. Third order. Maybe that works. I don't know. Any questions on that there? Yeah. All right. All right. So why don't you try one here? Let's do a typical problem, which is what is the rate law with the orders? What is the overall order of this reaction? And what is the value of the rate constant? So it takes some time. Here, use the table information there. See what you come up with. We'll start with the kind of generic rate law, if you will. So we got the, here. We have the rate is equal to K times our first reactant. And it really doesn't matter which letters you use, but most people use X and Y, so we'll use those to the X, and our I minus to the Y here. So again, we want to go to the table here, as we talked about, and basically choose 2 entries where one of them remains constant, the other one varies. So very easily you can see, looks like 1 and 2 will achieve that for keeping our first guy constant and varying our second. Again, I'm going to go with the larger rate up on top. So using experiments 1 and 2 here. That will give me 2.2 times 10 to the minus 4 equals K, 0.08 to the X, and 0.034 to the Y. Again, just putting everything experiment 1 up on top. That means experiment 1 up on top, everything experiment 2 will go on the bottom, 1.1 times 10 to the minus 4, K, 0.08 to the X, and 0.017 to the Y. Once again, we're going to do kind of our math here, so we'll end up with 2. Our constants here should be the same, so they should cancel. We kept these guys constant, so they should completely cancel, and that looks like maybe a 2 to the Y. That would mean Y in this case would equal 1. Questions on that? Because I did that, we do need to remember that that is the order for our I minus in this case, right? So now that we kept the S208 constant, we're going to go back now and vary it. and keep our I minus constant. And it looks like experiments 2 and 3 will do that. That's going to keep, again, our I minus here constant. So taking experiments 2 and 3, again, I'm going to go with the larger rate on top. So I'm going to put experiment 3 up on top. Again, you don't have to do that, but it just kind of gives you a little bit more whole numbers and decimals. So sometimes it's easier to do that. If you do it the other way, it should come out the same at the end as well. So we'll get 0.16 to the x, looks like 0.017 to the y. And everything for 2 here on the bottom, 1.1 times 10 to the minus 4, our k, our 0.08 to the x, and our 0.017 here to the y. Once again here, that is going to give me a 4. These guys will cancel. These guys will cancel. And that will give me a 2 to the x. Again here, x will equal 2 in this case. Again, if you're not sure, you can natural log 4 divided by natural log of 2 will give you 2 in this case. Yeah? Any questions up to that point? So we now have the order with respect to both reactants. That's going to allow us to actually put in here our proper rate law, which in this case, the rate would equal KS2082 minus, and that was the one that was squared, and our I minus here, again to the first order, which we do not write the 1. That means our overall in this case is going to be 2 plus 1, our third order. Yeah. At this point, again, we have an option to figure out the rate constant. We could absolutely choose any one of these, and they all should give us the same answer. So just to mix it up, I'll choose number 2 here to do that. And again, if you choose 1 or 3, should end up with the same value. I'm going to solve for k in this case for my rate law. So k would equal the rate divided by the S2082 minus. Again, I do need to square it. Divided by the I minus here. Putting in all our values here from the second experiment, that's going to give us 1.1 times 10 to the minus 4 molar seconds divided by 0.08 molar squared and 0.017 molar. And if we do that there, it looks like 1.1 to the minus 4 divided by 0.08, squaring it, and divided by 0.017. That's going to give us I'll go to the left here, 1.01. In terms of the units, once again, molarity on top and one of the ones on the bottom will cancel. That still leaves us 1 over molar squared seconds, which, as you saw in the previous example or the one before, that again is typically what we see here with the third order. You can see it's the same sort of units associated with the rate constant. Any questions on that? Yeah. For here, when you doing this, when you, no, you just need to choose one of the entries in the table. It doesn't matter which one you choose. So if you did number 1, you should get the same number. If you did number 3, you should get the same number. In theory, if you had a table of 6 entries, you could choose any one of the 6. The only thing that you can't do is, as I mentioned before, you can't kind of mix and match. So if you today's, I'm going to do this entry, you got to use all the information from that entry in there. Yeah. Other questions? So again, really, you can just see mathematically speaking, right? The rate constant, right, has an effect on the overall rate of the reaction, right? So if I had a large value for the rate constant, I'm basically be multiplying everything to the right by a large value, which typically will give me a larger rate, right? Than if I had a really small rate constant, I then would be multiplying everybody by a really small number, which would give me a much lower rate and stuff like that. So that's also sort of what the rate constant tells you. If you have a relatively, good number for it, you probably will have a significant rate that's happening. If you have a smaller number, obviously you'll have a little bit smaller one, just mathematically looking at. Any questions on that one there? All right, I think we will lay it up there, I think, for today.